Well, aloha, and I'd like to welcome you to the control charts screencast. Let's get started and talk about the ways you can construct a control chart, and we'll talk about the theory of control charts and why they help provide information about process improvement. Talk about which control charts you want to use for different types of data, and how to determine when a process is in or out of control. The basic theory behind control charts is pretty simple. First, we have to understand what a process is. So a process is a repeatable series of steps that are supposed to achieve a particular goal, like I'm manufacturing a product of some sort, or providing a service to a customer, or maybe providing some auditing duties. The idea is that there's a series of steps, and they should ultimately result in some sort of conclusive product or service, or achieving some goal. A control chart is simply a time series plot. Doesn't necessarily have to be over time, just any sort of sequence that provides the summary, a summary measure of some aspect of that process. So we might look at, as we're manufacturing something, we might look at the proportion of defects or defective products that get produced from that process. Or we might look, if we're servicing a customer, we might look at the average service time for servicing a customer. Or if we're auditing, we might look at the number of errors that are found in something. So whenever there's a process, there's going to be some sort of summary measure about the quality of that process. And if we look at a plot of those measures over time, or at least over some sort of sequence of that process, that's going to be a control chart. Generally, control charts are used for monitoring the quality of a process to see if it's performing as expected or desired, or for finding improvements to that process. A control chart is used to monitor the variation in that summary measure of a process. In other words, a control chart is used to view basically the variation of the quality of that process. Now, variations in a process, or at least the qualities of that process, could be due to chance or common causes, what we'll call normal variation or expected variation, because those are things that we can't do anything about, and they are expected to occur, meaning that they're just a natural part of the process. It's not something that would be actually considered a problem or needs to be perhaps investigated or improved. The other kind of variability that you might see is due to special or assignable causes. And these are things that are not necessarily inherent to the process, and they generally indicate a problem or area of improvement, and we might call that abnormal variation, unexpected variation. So when we see something in our process that's unexpected or abnormal, that could be an indicator of a particular special cause or assignable cause. So the difference is that chance or common causes make variability that if we look at the control chart, we would expect to see them. We'd expect to see that variability. We wouldn't see any sort of pattern that would be any different than what we would expect to see for any process. Any sort of departure from that pattern or expectations could be an assignable cause. The key here about the theory is that a control chart, if we're measuring or observing the variability of a process over time, we need to understand what is expected or unexpected. So we have to say what we mean by expected. So usually in statistics, when we talk about expected, it usually refers to some sort of average, some sort of central tendency. So that tends to represent what we'd expect. And so anything that sort of departs from that average or that central tendency would be considered unexpected. To make this more precise and meaningful, we actually have to assume a kind of a distribution. So whenever you have variability or chance or unexpected variability in data, we can represent that by looking at the distribution, which would tell us how likely it is that certain kinds of variations occur, or how much values would be, how much a value would be, how likely a value would be a certain um, amount, or over time how that value might be expected to vary would be determined by the distribution. So what we might need to do if we talk about expected variation or expected um, or normal variation, we might mean that to be that the variability in the measure of the process or the process quality varies according to some distribution that we know. It's very common to talk about something like normal variation, literally meaning that the variability in the measure of the quality varies like a normal distribution, like a bell shape. And that's what we mean by normal variation. And if we see patterns that do not look like they're normal or normally varying, we would say that it is unexpected variation or abnormal variation, and we might attribute that as an indicator that there's a process problem that's caused by some special or assignable cause rather than a chance or common variation. So if it fits the pattern of the distribution, we'd say that it's common. Anyways, that's the basic theory. Once again, we're taking sort of an a priori distribution as a way to describe how what we would say is expected. And that anytime we see anything that doesn't fit what we expect, we would say that that is an indicator of a problem by comparing what we observe to what we expect from theory. So again, this just means that we're assuming a distribution, something like that the variation is normally distributed. We'll talk more about that as we go. So when we have a process, we talk about the total process variation being a combination of the common or chance cause variation plus special cause variation. Now, variations in a process can be caused by lots of different factors: people, machines, methods, measurements, the environment changing. And we're interested in knowing when these factors are how much of these factors are attributing common or expected variation, and when is there unexpected or abnormal or special cause variation. So common cause variation are just, again, naturally occurring and expected. There's nothing we can do about them. They are resulting of just normal factors in the process, like if I'm looking at variations in machines for which they may perform slightly differently, or tool sizes, or temperature ranges, etc., or measurements, there's going to be what we call normal variation. And that kind of variability is generally assumed to be known and following a particular kind of distribution, such as the normal distribution. Special cause variation is unexpected and abnormal. It doesn't fit the pattern that we would expect or to see for a common cause, and therefore we think there must be something causing it. Because it doesn't fit what we expect to see, we think that there must be something different than what we expect that's causing it. So we'd say that it has an assignable cause, and that variation is not normal, and so we would try to find out what's causing it and how to correct it. So when we say a process is in control, we might look at some process measure over time, and we look for patterns. And the pattern, when we say in control, is that if we expect it to be varying, have expected variation, and we know that that expected variability is, say, normally distributed, we would just look to see if the variability that we observe is consistent with normal variability. So let's take an example right here. Let's just say that we're measuring oven temperature at a bakery, and that the average temperature for making our muffins here is this blue line. So that would be the average acceptable temperature and for baking the muffins. If we measure our oven at various different time periods, different bake sessions, we might see that the oven temperature was a little lower here, a little higher here, a little lower there, a little higher, a little higher, a little lower, relative to the expected or the average. Now, normally, if we assume that these temperature variations they're never going to be perfectly on the blue line on average, there's going to be normal variation. The thermostat doesn't necessarily kick in exactly at the time when we're at this temperature. It takes time to heat up or slow down. The environment outside might be hotter or colder than on certain days, so it might take longer to heat up or cool down on hotter days, etc. So there's a certain amount of normal variability. If we assume that that variability from this average is normal in terms, literally meaning that it's a bell-shaped distribution, then we would expect to see most of these points very near the blue line. Not necessarily on them, but typically they tend to be near them. So if the variability in temperature is normally distributed relative to the mean here, we know that based on the characteristics of the normal distribution, that if we were going to be that a value that's more than 3 standard deviations away from the average from this blue line would be very, very rare, very unlikely. So in other words, if we're higher than 3 standard deviations above the blue or lower than 3 standard deviations below the blue, that would be considered unexpected. In fact, we define that as an outlier for normally distributed data. So if you have these control lines, this upper control limit and these lower control limit, you'll see that these are placed exactly 3 standard deviations above the mean and 3 standard deviations below the mean. So if we have a measured value that's below the lower or above the upper, it would be more than 3 standard deviations away from the blue. It would be considered an outlier or an unexpected or unusual point or abnormal. It would happen, such points shouldn't happen more than 1% of the time, and that would be rare enough for us to consider the process not in control because it's outside these control limits, meaning that the values are unexpected. But there's other things that could be unexpected or expected. So if it's normally distributed with this number of points, there's only 1, 2, 3, 4, 5, 6, 7, 8, 9 points here, we certainly wouldn't expect in 9 points that any of them would be over the limit, the control limits here, or more than 3 standard deviations away. Also being normally varying, we would expect that about half the time we'd be above the mean and half the time we'd be below. That's because the normal distribution is symmetric about the mean, and as the left side looks like the right side. So we would see that about half these points should be above and half should be below. We see 1, 2, 3, 4 above, or 5 above, and 1, 2, 3, 4 below. So there's about the same number above the mean as below the mean. So it's sort of symmetric in that. We wouldn't expect any biases. We wouldn't expect to see a whole bunch of them in a line above, because what that would mean is that as we are going above, as we go equally, we're just as likely to go higher than the mean as lower than the mean here. So we might go up here, but we expect it to go down the next time we go up here, and we expect it to go down. It did go down, and we went down below the mean here. So we would not expect a lot of them to be above here in a row. We wouldn't expect anything to continue to go up, 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 or down, 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 down. We expect it to kind of bounce up and down and up, up, and then down, 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 and then up and down and down. It shouldn't really go up too much or down too much in any time, and we shouldn't see any more above the mean than below the mean, or others would be skewed. So we don't see any skewness, we wouldn't see any kurtosis, and we wouldn't see any rare values above or below the control limit. We don't see any of that here, so we'd say the process is in control, or at least there's no indication that it's not out of control, and the way that these points bounce up and down seem to be normally varying, and normally we mean as in the normal distribution varying. So going back to the control limits, one of the first things you want to look at with a control chart are the control limits, and the control limits will always be defined as points or values that would be considered unexpected or unusual or kind of outliers. And so if we expect that the process is normally varying, we might see something like a bell-shaped here. You see that the mean is right here in the middle, and higher values are less likely, lower values become increasingly less likely. As soon as we hit 3 standard deviations above this mean, we're very rare. Same if we're 3 standard deviations below the mean, that's very rare. So most of the values should be between plus or minus 3 standard deviations. In other words, if we're above one of these control limits or below one of these control limits, we would have an outlier, and that would be an indicator of a problem, probably due to an assignable cause. Notice here that the combination of 3 below and 3 above is 6 standard deviations, or what we call 6 sigma. And you might have heard of a process improvement group called 6 sigma, and they are called that because of exactly this. They're talking about making sure processes perform within 3 standard deviations. So the control limits are defined as plus or minus 3 standard deviations simply because in a normal distribution, anything beyond that would be considered an outlier and very rare, and indicating a possible problem or a deviation from normal variability. So in other words, as long as we're in this tan region here, it's expected variability, and anything outside of it in the blue here would be unexpected variability, because it should happen less than 1% of the time according to the normal distribution here. So our first rule for special cause variations is if we see any points above or below the control limits. Once again, we know that if we're above the control limit here or below the control limit, that should happen less than 1% of the time. In other words, 99.7% of the values, that's almost 100%, should be within the control limits. So if we're outside of it, especially with this few points, it would be considered unusual. The only time that we might actually expect a point outside a control limit is if we have a whole lot of points. So if 99.7% are expected to be in the control limits, if we have, say, 100 points, then 0.7, we might actually consider that we have one, and 100 points here, we might have one that's over the control limit, upper control limit, but lower than the control limit. More likely like 200 or something like that, then we would expect it. But here we only have like 10 points. And so in 10 points, we certainly wouldn't expect any of them to be above or below. So we say a process is not in control when we see a pattern that causes abnormal variation, or that doesn't follow what we'd expect from normally varying values. So sort of the 3 rules to look for, and the variations of this too, are that, and again, these are more or less based on how likely something is going to occur, and some people have more tolerance than others. So some people will look for a much more rare event to say that it's something unusual, or they might look for something a little less rare if they're being more conservative. But generally, if you have anything outside of the control limits, that's plus or minus 3 standard deviations, that's considered an indicator that the process might not be in control or has abnormal variation. If you look at 8 or more points in a row on one side, or the center line or the mean line, that also might be considered abnormal variation. That pattern would not be expected if data was normally varying. Similarly, 8 or more points moving in the same direction, either all up or all down, also should not be is unexpected. The general thing to think about in terms of processes not being controlled is that any pattern that is unexpected, if it's due to chance variation. In other words, we can look at what the variability is in terms of random variation, and we can figure out just exactly, if we assume a distribution of what that chance variation is, and if we see something that doesn't meet that pattern of chance variation, we would say that it's an indicator that it's out of control. The thing to keep in mind is that the rules are not laws. So just because something violates one of these rules here, that we have 8 or more points on one side or a point outside the control limit, doesn't necessarily guarantee the process is out of control. It only indicates that the process might be out of control. It indicates that there's something unexpected there and it needs to be investigated. It's always possible that such a thing could have just happened by chance. It just happened to be its time to come up. And also you need to keep in mind the sample size. The more data points you have, the more likely that rare things actually will occur. So you can imagine that if I flip a coin 10 times, it's unlikely that I'm going to get 10 heads in a row, right? But if I flip the coin 100 times, it becomes more likely because at least I have 10 opportunities for that, right? And if I flip it 1,000 times, it becomes even more likely that 10 heads would happen in a row. And if I flip it 1,000,000 times, then, there's a pretty good chance that you're going to have 10 heads in a row. Something to think about. So visually, the rules look something like this. You already saw rule 1 where you're above the upper control limit or below it, 3 standard deviations away from the mean, for example, if it's normally varying. Rule 2 looks something like this. I might see 8 or more all below the line or all above that. And so you can think about this, that the fact that this goes up and down and up and down above the mean line says that you kind of have a 50-50 chance of going above it or below it. So here I'm below it and I have a 50% chance of going above it, but I'm not. So again, when I'm here, I have another 50% chance to go above or below, and I stay below. So 50% times 50% would be the probability of staying down here. Another 50% if I stay down here again. You see that this is getting smaller and smaller. So 0.5 times 0.5 times 0.5 keeps getting smaller and smaller and smaller. When you get 8 in a row here, that's 0.5 to the 8th. That's 8 times that you multiply 0.5 together. It's a very small number. In other words, much less than 1%, and you wouldn't expect that to happen. A similar idea goes like this. If I have values going up, 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 a trend upward or a trend downward, these trends are also, if the data is normally varying, unlikely. Once again, we're just as likely to go up after a value as to go down if it's normally distributed. And here I'm flipping a coin and I go up. I flip a coin heads and I go up. I flip a coin heads and I go up. So it's just like flipping heads, 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 heads. And again, flipping that many heads in a row would be unlikely. Same as this. So again, the likelihood of this happening is very small if the data is normally varying. And so if it doesn't, we wouldn't do that. So if it's determined that there's an indicator, if you violate any of these rules, it indicates that there might be abnormal variation. We might want to see if there's a cause. Is there a special or assignable cause for making this be lower than the average? Or it was something that's making this increase when it shouldn't? Or is there something that made this one go over the control limit? If we can't find out what made it, it could have just been chance. But if we do find an assignable cause, then we'd say the process is out of control due to that particular reason. So reiterating, just because we violate one of these rules doesn't mean the process is out of control. You need to try to explain other evidence or other reasons why it would actually be out of control. These are only indicators that there might be. You have to think about other factors. So control charts come in a lot of different flavors depending on the kind of data you're working with. So the ones that we're going to talk about, the main ones, are P charts, C charts, mean and range charts, individual moving range charts, or individual X and R charts, they call them. And the kind of chart that you would use is depending on the kind of data for the problem you have. So if you have data that counts stuff, if you're looking at a process that the quality measure or the summary measure is counting something like the number of defects, that's going to be categorical data, and we're going to use a P chart or a C chart. If we're measuring something, say we're looking at the temperature of something, or the weight of something, or the amount of time it takes, or how much something costs. If it's a numerical data and we're measuring something, then we're probably going to use a mean and range charts or an individual X and MR chart. So let's look at the kind of problems we might have. So a P chart actually stands for proportions, or a proportions chart. So if we have data that we are counting, usually from a categorical variable, and we're just counting how many are in a particular group, like we might be counting the number of defects, like how many of these products were defective. And if you divide that by the total number of products manufactured, or at least in the sample, we get a proportion. So if we count the number of defects out of a particular run, and we look at the number of things in that run, that would be a proportion. If we plot those sample proportions over time, we could see what is the proportion of defective things over time, and we could see if it's normally varying or not. So typically what we're going to do for a P chart is we're actually going to assume a binomial distribution. Binomial distribution is kind of like a discrete version of the normal distribution. So because we're talking about counting whole things, not measuring something, we usually don't want to use the normal distribution per se, because that doesn't represent well the kind of variability we'd have when we're counting whole things. But the binomial distribution is a good way to do that. Turns out that there's a very close relationship between the binomial distribution and the normal distribution. You can actually approximate the binomial distribution very well with the normal distribution, but that's a subject for another time. All we care about is, if we're using a P chart, is that we're counting things and we're looking at the proportions. And that means we know what the sample size is. If we're sampling something and we look at the number of things that are defective or unsuccessful or whatever it is we're looking at in terms of the quality of the process, and we divide it by the sample size, we get a sample proportion, and we plot those over time. To make the assumption of normal distribution work for the control limits, we need to assume that the n is the number of things and p is the average proportion, or the sample proportion. We need to make, or p would be the number, the proportion of things we have. So we need to make sure that the number of points of the proportion that we have times the number we have is more than 5. This is a very mild thing. It's almost always okay as long as you have enough point. But this basically just says we have enough variability to actually determine what binomial distribution actually sets the limits. In practice, it won't be a big issue. A C chart is very similar to the P chart, except for we don't have a sample size, or the sample size is fixed. And so we still are counting things, and so it's whole numbers, and we're still looking at categorical variables or data. And we just look at the absolute frequency. So if you just plot the absolute frequency of things over time, that will give us an indication of whether it is in control or not in control. You might find it curious to see that the Poisson distribution is the underlying distribution that we're going to assume for normal variability. In other words, we're going to assume that the variability in the counts of these things are according to the Poisson distribution. If we don't have, and so it's going to be used to calculate the control limits. And so if we see anything above or below the control limits, those control limits will be calculated according to the Poisson, like 3 standard deviations above or below that. But it's not the normal distribution. Sometimes you have to use a C chart because we don't have the sample size available. We only know the count of how many things, and we're always counting the same number, even if we don't know what it is. Moving on to mean and range charts, if we have measurement kind of data, typically time or weights or lengths or volumes, etc., then we're going to actually calculate two charts. We're going to look at the range, which is the minimum of the maximum. So we might have a sample of data. We take that sample of data for each time period, and we calculate its mean, and we calculate its range. And the mean and the range chart will show you all the ranges of the samples, the max minus the min. And the X bar chart will show a plot of all the means of the samples over time. And again, you look at those, and we will assume that the normal distribution dictates what normal variation is. And so if we see anything above or below the control limits, that would be more than 3 standard deviation above or below and considered unusual. And it would be the same for both of these charts, the R chart or the X bar chart. We assume that the variability in both the range and the means are normally distributed. Turns out for most sample data that if we have numerical data and we have actual sample sizes, that a range and assuming that the variability for the range and for the sample averages is normally distributed is actually quite reasonable. Many people are concerned about that, but it turns out to be not a problem at all. If we don't have samples, maybe we only have one measurement per time period, so we can't look at a mean. We can't look at the sample mean. There's no range because there's only one measurement per time period. We can look at the individual X and moving range charts. So what we'll do is we'll just plot that measurement over time, and we'll plot a moving range. We'll look at successive measures and look at the differences between them and see how big or small those are. Now, it turns out that those control limits don't assume it's normally distributed, but it's a little complicated, so we're not going to talk about exactly what it is. Just know that it's not necessarily something we assume is normally distributed. Okay, so I think we should take a look at some of these things. Let's take a look at an example of a p-chart now that we've introduced it. So I'm going to open up here the p-chart example. And let's see, here it is. So looking at our p-chart example, you'll see that I have some data. Now this is data for, I think, trades. So this is looking at, I have some data here on various different days. I look at the number of trades that were canceled or with errors and had to be resubmitted. So those are bad trades. And I look at the total number of trades. So these are sort of the defects, and I can get a proportion of trades that were no good by looking at the number of bad trades divided by the total number of trades that day. 2 divided by 24 would be the sample proportion. So if we look at those sample proportions here, like 2 divided by 74 here. Okay, so this would be the sample P, right? We could do this for all of these guys here. Oh, I should not have done that. I just made a mistake. Don't hard code your data, folks. Take that divided by that. There. Okay. And if you plot all these over time, all I have to do is do this and insert the time series here like that. You'll see I've got a p-chart. So this is a p-chart here. I'm looking at the sample proportions over the days. And what I need to add to this to make it a good control chart is I need to understand what's the average proportion and what are the control limits. You can calculate the average proportions just by looking at the average of all these. The control limits are a little more complicated. They're actually defined by here. You see these formulas here. So you don't have to worry about them, but this is the binomial limits for assuming the binomial distribution. So you see that it's all calculated for here. I have my trade data here, and I look at the number of samples, and I have a little plot here with the control limits in here. So here's the average proportion of undesirable trades, which is 0.119, so about 0.12, about 12%. I'd say are on average defective or undesirable. I have my upper control limit here is at 22%, and our lower control limit is 2%. Now, as we look along here, we see that 1 point is over the upper control limit. That's kind of worrisome because we have about 30 days of trading here. In 30 days of trading, we still wouldn't expect anything to be above the control limit here. So this is a point perhaps that would indicate the process is out of control, and we should investigate to see if there's a special cause to this. Is there something that happened on this day, day 4, that caused a higher proportion of undesirable trades? Looking along here further, you see that there's one that's below. Some of them are pretty close, which is a little nerve-wracking. We should maybe want to look at that. But here we have a point that's below the lower control limit. In this case, I'm not actually going to say that it's an indication that the process is out of control, simply because the problem is defined that it's the number of bad trades that were in error and had to be resubmitted. And in this case, what we're saying is that there was a much lower proportion of defective or undesirable trades. That's a good thing. So that doesn't actually indicate my process is out of control. I might want to go look at what happened on this day that kept my number of undesirable trades really low, and that might be something I might want to repeat for improvement purposes. So here I might have an indicator of a problem in my process. Here this might be an indicator of something that we can do to improve our process. Here this indicates out of control. This one does not indicate something that's out of control, simply because it's actually a good thing. We're looking for other patterns. We look for trends going down or up for 8. I don't see any of those. And I see about half are below and half above. I could count them, but I'm also going to look for any sort of runs where there's all 8 above or 8 below, and I don't see any of those. I see this run of 1, 2, 3, 4 going down, but then it goes back up again, so we're okay. And I don't really see any more than 2 below. Here's 3 below. 1, 2, 3 below. That's about the longest below I have. Here's another 3 above. 1, 2, 3. So nothing worrisome. The only concern is this point here, which should be investigated. Okay. Let's take a look now at a C chart. So C chart would be just counting things. So looking at our C chart example. So I think our C chart example, reading the problem here, it's always important to understand the context of the problem so that you know what it is. It says, we've determined 34 different 10-foot sections of aluminum sheeting, and we're looking for any that are defective, and we count the number of defects in the 34 different 10-foot sections. So the sample size is fixed, and we're counting the defects per unit. We're not using examining to see if the units in themselves are defective or not. So like the P chart, we'd be counting the number of defects per unit, but now we actually want to see how many defects we have. So we're going to use a C chart to see whether the number is out of control or not. So here on various time periods that we've sampled it, we found 1 aluminum sheet, 4, 7. Remember, they're always out of 34 here. So plotting these over time, and then looking at the successive differences. So plotting these would be the C chart. We see that the process looks pretty good. So we see nothing over the high control chart, high upper control limit, and the lower control limit actually is at 0. But once again, because low numbers of defects are good here, that we don't consider anything that down here as an indicator the process is out of control. So see, we had zeros here. Those are not a problem. Those are not an indicator. Nothing above here, so they're okay. So now we're looking for any sort of runs. Do we see any runs going up or down? We have 1, 2, 3, 4 up. That's no problem. Here's 1, 2, 3, 4, 5, 6 up. That's not a problem either. So we don't really see anything that's indicative of a run up or a run down, and we also don't see any 8 above or 8 below, and we see about half above and half below. So this process looks like it's under control. The one thing we need to ask ourselves is that we have this average here. See the middle line here? The average number of defects is 4.382, about 4.4 defects or defective aluminum sheets. We have to ask ourselves whether that average makes sense. Is it okay for us to have about 4 defective sheets out of 34 possible? If it turns out that that's not a problem, that we can tolerate that number of defects, then the process is fine, it's under control. If it turns out that that seems to be an intolerable large number of defects on average, then we need to look at how to improve our process. So simply, even though this might be fitting our patterns that we have expected variability, the whole process itself might be off if our average is not acceptable. Okay, so that shows that. And now we're going to look at mean and range charts. So mean and range charts, we will measure something. So let's see what we're going to measure here. Now, mean and range charts are often called X bar. X bar, meaning an X with a bar over it, is usually the notation for the sample mean. So that's why they call that the X bar chart, because it's a sample mean, and R stands for the range. So here we have sections of water pipe where we do 3 stress tests on 23 sections of them, and they were randomly selected. So we have 3 observations each. Stress 1 and stress 2, I guess we have 2 different sets of stress tests, and so we get various measurements for observations. So we have a sample size of 3, and we have 2 different data sets here. And so what we would do is look at the mean of these, right? And so that would just be the average of this sample, right? And then we'd also look at the range. The range is just the max, a max of the sample minus the min of the sample. Remember, the range is a measure of variability. So we're looking at a central tendency and a measure of variability here, and these are the things that we'd plot on our control charts, and we'd like to see if these are normally varying, and we'd also like to see if these are normally varying. Okay, so taking a look at what we have here, okay, we have these results came from Megastat. We see that the sample mean, or the X bar chart, have the average here of 458.17, and we have an upper control limit and a lower control limit. That's 3 standard deviations away, and we see right away that there's something that's kind of on the control limit. This point looks suspicious. It's unusual or unexpected. It means that we have a higher stress than average, much higher stress, and unexpectedly higher stress than average. So we should look to see if there's a special cause assignable to that. We also see some runs 1, 2, 3, 4, 5, 6 below. That's okay. 1, 2, 3, 4, 5, 6, 7, 8. So see this run of 8 below here? That's also unusual and unexpected. We should not see 8 all below this line here. So the fact that we have higher than expected stress at the control limit, about 3 standard deviations away, and that we also have 8 that tend to be below, seems to indicate that our process is out of control. And we should try to understand what caused this to go here and what caused these to go down there, and see if we can fix it. Now, one thing to remember is that when you see problems in measurements of your process, you always have to think of the possibility that the measurements themselves were in error. So it could be that the process is out of control, or it could be that the process measurement was in error. And if we examine the data more closely on this one, we found that maybe the data actually was measured wrong. Now mean and range charts go together. So when you're looking at X bar and R charts, you look at them together. You typically look at the range first and to see if that's in control. If that's in control, then you look at that. If the range is out of control, then the whole process is going to be out of control also. So looking at the range chart, we see quite clearly on this point here, which is the same point up here, the range is way off. And so this is an indicator that the process is out of control. Looking at these ranges here, you see we don't see any 8 below. 1, 2, 3, 4, 5. That's pretty close, so that's okay. So here we don't see any 8 below or above. We don't see any trends up or down or 8. We only see this one above. So this is the only indicator that there's a process out of control. So the fact that we see that this is out of control and that looks like it's out of control means that we should probably investigate. For the second set of stress tests, stress 2, we see that everything looks pretty good in terms of the control limits. That's a short run below. This is also a 1, 2, 3, 4, 5, 6 below, also kind of a run down below 6. So it's a little suspicious, but okay. Looking at the range chart, which is again we should look first, we see everything's in the control limits, no runs above, no runs below, no trends up, no trends down. So this process seems to be under control with respect to normal variability. So we would suspect that the first stress test observation, something's out of control, and the second stress test, they're in control. So this one here is the one we're going to have to look at more carefully. And lastly, but not leastly, the individual range and move charts, or the X and MR. So opening up the X and MR example, okay, ignore those links. Looking at the data here, we have data that represents what? Whoops, let's see if we can see that. This is unloading time. So we're unloading the times it takes to unload some shipment boxes. And so we just have single measurements. We don't have a sample of unloading times. We just said that on this delivery it took us that time, that delivery took us that time. So we can't really look at the mean, although we might say that the mean is 20. If the mean is unloading is 20 minutes, we might calculate a standard deviation of plus or minus 3 standard deviations. And so we make the control bar at 20. And 3 standard deviations above or below would be these upper and lower control limits. Looking at this again over time shows us the individual unloading times seem to be normally varying. The moving range is where we simply look at the differences between the two. So the moving range, we'll call it MR. We have to start below. It has to be this one minus that one. Okay, as you can see, we got a 10 there. And we might look at the absolute values of the ranges here, but it's not necessary to do that. It doesn't matter which way you go. You can go one versus the other. And you can see we get a bunch of moving ranges here. So we can look at the chart here. Here's the individual chart, just the same as this one, just reprinted differently. And here would be the moving range chart. So if you look at the moving range chart, we're always going to have one less point because we're looking at successive things. And here we see that something is approaching the upper control limit, but it's not so bad. And we don't see any particular runs above or below, and no trends going up or trends going down. This point here does seem to be abnormally low, but again, keeping in mind that this range is about counting unloading times. So if the unloading time between one unloading and the next unloading time were exactly the same, we're going to get 0. So that's actually okay. An unloading time of 0 is fine. It's only when you have a big difference in unloading times that we might be concerned, not small differences or no differences. So that is it. That concludes our screencast on control charts. We've talked about various different kinds of control charts. The basic way you decide which control chart to use is first understand whether you're looking at categorical or numerical data, or i.e., are you counting something or are you measuring something for your process? And you want to make sure you understand what it means for that measure that you're making to be high or to be low, and whether both either being too high or too low relative to average is bad, or only being high or only being low is bad. And then you can calculate and assume, based on an assumed distribution, what you would expect the normal variation control limits to be. So we looked at various rules for determining whether a process is in control or not by indicating patterns that are unexpected variability. And we looked at some examples in Excel. In class, we'll actually do some of these control charts and solve problems with them. So I hope that this has been good for you, and I will see you later.